This is the AI Travel Companion Group, and today we are going to present our demo for DSCI560 Lab8, and I will be presenting the first part, accuracy comparison of duct-to-vec embeddings, and my teammates will present the next two parts. So first, let's have a look at the duct-to-vec approach. We started by loading our dataset, which is a collection of travel-related Reddit posts from previous lab, and we can have a look at the data. So the data includes the ID, the title, the body, the keywords, and the image tags. So we used the title, the body, and the keywords and the image tags for duct-to-vec analysis. We parsed and tagged the documents and then tried 3 different duct-to-vec configurations, and mainly varying the vector size. So we set the vector size as 50, 100, and 150, and try to get vectors for all the documents. And after generating the vectors, we normalized the vector and applied k-means to group similar posts together. And to determine the optimal number of clusters, we use the Sihuat score, which measures how well each data point fits within its cluster compared to others. And it turns out that the best case was 2 for all the vector size, and then we save the cluster labels for further analysis. Next, we perform a qualitative evaluation. So we randomly sampled 10 sentences from each cluster and examined them to understand what type of posts each group contained. And we also reduced the dimension to 2 dimensions for visualization. And here are the results. When the vector size is 100, the 2 clusters are separable, and when the cluster size is 50, the clusters are still separable, but there is a little more overlap. And when the vector size is 150, the overlap becomes more noticeable. And based on the Sihuat scores, for vector size of 50, the score is 0.11, and for the vector size of 100, the Sihuat score is 0.1244, and when the vector size increases to 150, the score drops a little. So by combining these results with the visualization and examples, we found that the duct-to-vector model with the vector size of 100 achieved the best overall performance, followed by 150 and then 50. And in terms of the content, the cluster 0 mostly includes posts about travel planning and advice seeking, while cluster 1 focuses on the travel experiences and reflections. So that's all for the duct-to-vec analysis, and my teammates will present the next 2 parts.
Okay, this part of the video goes over the word-to-vec code for DSCI560 Lab8. This is part 2 of the lab. So we have a word-to-vec Python file here. Initially, we're just reading in the data as JSON, and this is the Reddit data. So if we take a quick look at that file, each individual JSON in this file corresponds to a Reddit post. So we're just reading in all the Reddit posts here. And then for all the posts, we're tokenizing the text. So we're creating the necessary tokens to then create the word-to-vec embeddings. So in order to create the tokens, we're leveraging this simple preprocessed function from Gensim. And we're using the title, the body, and the keywords that we extracted from each Reddit post. Then we're evaluating 3 different vector sizes or dimension sizes, 50, 100, and 150. So these are used for 2 purposes. First is for the vector size of the word2vec embeddings. As we can see, we're passing it here. And then once we have the embeddings created with word2vec, we are clustering the words into bins, and we are using that same vector size as the number of clusters. So we're basically running k-means with the word embeddings from word2vec for the current iteration. So we basically repeat the same process for each of the sizes that we have here. So we repeated three times. So after we have the clustering of the words into the vector size bins, we then build the document vectors. So basically for each document, we count how many words fell into each bin, and then we normalize by the document length. So at the end, all documents become basically vectors of length, vector size. And then, so that's this section here basically. And then finally, we're running k-means clustering again, but now on the vectors, and we're doing it based on the silhouette score of the clustering. So that's this final part here. And then this part at the end is mostly just printing out the the visualization that we created, so the plot that I'll show in a second, and then just printing out some metrics just for analysis for each iteration of the vector sizes. So once we run this code, which we just have to run the Python file as is, well, we install the requirements file and then we just run it. We don't need any extra parameters or anything. That's going to generate these results files. So it's going to create one clustering plot for each vector size. So those 3 right here, and we can see the results. And in the next part of the video, we'll go over the analysis of these results and the comparison with the results of doc2vec. Thank you.
Hello, in this session, I will compare and contrast the difference between word2vec and dot2vec critically. The most efficient and accurate ways of comparing the accuracy and performance of embeddings are to test their performance in real applications. Hence, in order to compare the performance of word2vec and dot2vec, we will use 2 ways to evaluate their performance in the k-means clustering task for custom Reddit post. As a result, k-means clustering using word2vec and dot2vec with dimension 50, 100, and 150 are implemented respectively. The first evaluation method for comparing k-means clustering is silhouette score, which examines how closely samples are inside the cluster and how far samples are across clusters. The closer to 1, the better the clustering result is. The table below displays the silhouette score of k-means clustering using these 2 embeddings. This is the score for word2vec and this is the score for dot2vec. This table shows that word2vec outperforms dot2vec across all vector dimensions, since the silhouette score using word2vec are closer to 1 than using dot2vec. Moreover, the clustering visualization also confirms this. The visualization map of clustering results is a more intuitive and direct way of displaying the clustering performance. Figures below are k-means clustering results using these 2 embeddings. This is the result using dot2vec and this is the result using word2vec. This figure displays that clustering using word2vec are mostly clear spatial separation between clusters, while dot2vec suffers from more overlap between clusters at all embedding dimensions. Overall, within each embeddings, word2vec performs best at 50 dimensions with the highest silhouette score and the cleanest boundaries. Dot2vec peaks at 100 dimensions but still shows mixed clustering results. However, both embeddings degrade the clustering results at dimension 150, which might be because of the curse of dimensionalities. Additionally, at dimension 150, dot web maintains some balance with increased overlap, but vertical collapse into one dominant cluster. In conclusion, vertical models with 50-dimensional embeddings provides the best clustering for this dataset. This might be because DotVet learns embeddings by using dot vectors to predict all words in the whole post. So it is more likely to capture post overall semantic meanings. However, DotVet learns embeddings based on words frequency and by predicting each word independently using its neighboring words, which preserve local semantic meanings and details. Already posts with clusters are from the same chip topic, so they have similar overall meanings. To cluster similar posts into more cohesive and smaller clusters, such as cluster for chip planning and cluster for chip experience, the difference of local details among posts are more important and useful in this case. Moreover, most ready posts are short, which cannot provide enough information for DotVet to run accurate semantic meanings. Hence, DotVet has expected better performance in these ready chip post clusterings. Thank you. This ends all sessions in our lab.